These are the only two that I can say with complete confidence that we know, and I'm mentioning them because they will come up time and again, and they are kind of the special values. So remember I drew this picture of natural log earlier? Right, y equals natural log of x. And it turns out that when I plug 1 in, that's actually this intercept here. So natural log of 1 is actually 0. Natural log of e, I don't know, it's kind of hard to write these, but natural log of e is actually 1. And the reason is, and I think the reason too also why we maybe don't feel very comfortable all the time with natural log and what it is that it's really an inverse function. It's the inverse of e. Does this sound familiar? So like this is natural log, and if I drew this picture, this is e. And I think we feel pretty good about plugging things into e. Well, about plugging like 0 into e, say. What's e to the 0?
1.
Yeah. E to the 0, like any number to the 0, is 1. And so the reason natural log of 1 is 0 is because this is the inverse function, right? So whenever we plug into e and get out, we swap the inputs and outputs. It's like flipping over the diagonal, maybe easy about. So this is the same idea where like, what is e to the 1? Well, this is like that exponent we don't always write, right? Like 3 to the 1 is just 3. E to the 1 is just e. And so that's why when I plug e into natural log, I get out 1. But I would say these two values, so natural log of 1 being 0, natural log of e being 1, those are roughly the only two values that are nice for natural log, and this can be useful. Because now, what does that mean? What should I plug in here?
0.
0, 1. And now this is like the world's nicest integral. What do you get when you integrate? You get u to the what? 7. And what else?
Over 7.
Over 7. And we're evaluating from 0 to 1. So what do we plug in first? We plug in the 1. 1 to the 7th is 1. And so we just get 1/7, and then we would subtract plugging in 0 by 0. So that's it. It's 1/7. Yay. Any questions about this? So maybe something that I'll point out, if you ever get confused too about like which order do we plug these in, math is just like English, where you read like top to bottom, left to right. Right? Like if you're reading a page, you're like reading across the page and you work your way down. So anytime you see things like this, top to bottom, left to right. Like we just read it like we're reading English. It's not Hebrew. Or Arabic. Does Arabic know words? Do you guys know? Arabic. Alright. Okay. Did anybody try this for number 10? Do we feel like we could do the u substitution for number 10, but maybe we're done with the bounds? This problem, right? What do we try for u?
X squared.
Why is that a good u?
Because
It's a function inside of a function. It's x squared is inside of the e. And what happens when you take it to u? divided by the 2. And then what happens if you change everything into u's? You've got e to the what?
To the U.
E to the u, and what else is in here?
1.
Yeah, 1/2 in the du. And then if we were trying this bounds changing business, what are the bounds we're changing?
1, 0.
Yeah, we're changing 1 and 0. So where do we plug the 1 and the 0 in to see what they change it
Yeah,
to?
expert.
Yeah, into the x squared. So what happens to them?
They convert to U.
Yeah, so now they convert to u, but like u is, yeah, 1 squared, which just is 1, and 0 squared, which just is 0. So in fact, this was kind of like a special problem, which is kind of cool, where the bounds actually don't change at all. And so the actual definite integral of these two integrals, it gives you the exact same answer, which, I don't know, it's kind of crazy that that happens. But then this is super nice, right? Because what's the integral of e to the u? E to the u. And then I plug in my bounds, and this is like 1/2 e to the 1 minus 1/2 e to the 0. Well, what's e to the 0? 1. So this is like fully simplified. Maybe you have the 1s and 0s plugged in, and you're not fully simplified, that's fine. But yeah, this is very nice. Questions about this one? Alright, so the last couple, I just wanted to talk about 2 more of these that we haven't talked about yet, 6 and 7. Have we thought about 6 and or 7?
Yeah.
Okay. Okay, so we've thought about them. Now maybe we can kind of finish them or see. Oh, actually, before we do that, there was a really similar integral to this one, right? X e to the x squared. What was the similar integral? Maybe like x squared e to the x. These looked really, really similar. Does anyone try? I know you have an answer, Karen. Did anybody try like doing this one, or thinking at least like? So it looks really similar. Can you do it the same way? What is really different about this problem?
The function would not be the function outside. The function inside the function would not relate to the function outside.
Yeah, so you're saying inside, like here I've got, this is my inside, and it works great as a U substitution. Do I have a nice looking inside function here? I don't. So in fact, this problem, this is not a U sub. And the way that it's done is actually a method that you learn in Calc 2. But the point kind of, I guess, I would say, like the summary, is this has an inside function, so it's U sub. This is actually a product. So if you think about, like U sub is kind of undoing the chain rule, you might have had a question like, well, what undoes the product rule? This sort of problem that has a product in it would need that kind of anti-product rule, and that's what you learn like the first or second day of Calc 2. So, any questions about that? I just wanted to point it out because there are a lot of very subtle, like, it has almost all the same symbols in the problem, they're just like slightly rearranged, and it makes for a totally different problem. Alright, so, oh, are you stretching? So here are 2 that I think we can agree look like pretty similar. It's a number over x plus or minus a number. So I know I talked with you guys about this a little bit. People who, I don't know, thought about this, did people think about this problem and like what you could do? Did you have an idea, Karen?
Yeah.
Yeah, do you want to share? You can even just tell me.
I did D substitution.
Okay.
So U would be X minus 4.
Okay.
D would be dx.
D would be X.
And then you plug this in.
Okay, so then what happens?
It's another 3.
Okay, so you like pull the 3.
Yeah.
Uh-huh.
So it'll be 1 over U D.
Excellent. Okay, so that's great. And then what?
And then you just integrate.
Yeah, and so what do you get?
3 times
Okay. And then what?
you plug in.
Okay, great. So then you're like, cool. I plug in the x minus 4, and I'm all done. Okay. So how do we feel about this? Do we have questions about, like, I don't know, like why did you think to do a U sub, by the way?
Because I know the derivative of x is dx. If there's an alpha.
Yeah, so it kind of just takes care of the badness of this minus 4. Okay. Yeah, so I think a lot of times, like when the denominator is not quite what you would want, like if the denominator was just x, you wouldn't need the u sub at all, right? You'd be like, oh, it's just 3 natural log of x, and here we got this. So, in general, like you can do this a lot of times. Maybe I'll erase this for just a second. Bounds for just a second. And if I looked at this problem, I would see that this problem is like virtually identical to this one, right? And so if we were going to do Karen's method of solution, what would we be doing here? Okay, so now you're kind of jumping us to the end where you're saying like, look, if I had done the u sub, it would be like in here, but the du is just dx, so it didn't actually like change anything, and I just kind of like jumped down to this answer. And this is great. You can do this every single time, and you guys will see a lot of problems. Maybe I'll even like make it quote trickier. You could have an integral that has like some number a over x plus b dx. So like a and b are just whatever numbers. So based on this, like okay, we don't even need to really do the u sub, we can just jump to this final answer. What would be this integral? A ln of x plus b. That's it. So this is another problem where like, I think you don't do a whole lot of problems that look just like this one in Calc 1, but you do a whole lot of problems that look like this one in Calc 2. There's like a whole section where your answers are going to look like this. And now, if you are like, this kind of went fast, I'm unsure, you can always do the u sub and finish the problem. But over time, this is another one that I would say you develop like, okay, I just do it like this. So what happens, I erased the bounds from this problem. What happens if I really did have these bounds? That was 3. Yeah. How would I go about evaluating this? Or like, is it okay to just do my antiderivative and so here's a question. Is there anything strange about these bounds and this function?
Negative.
-2 can't go in the function right now since it'll make it up.
So if I plug -2 in, this bottom is going to become 0. And that's not okay. So far, in Calc 1, you kind of live in this very happy world where every problem they give you, you can do. They're like, here's an integral, do it. Plug in these bounds. It's all good fun. in Calc 2, you guys will get to the point where you cannot plug in, like your bounds don't work for the function. So all of this, like this happy world of the integral from a to b of f of x dx being f of b minus f of a only works for like good bounds or good functions. If your function's continuous, everything is happy and you can plug in whatever bounds you want. But this one, in fact, this is not quite right. And you will develop some ways of dealing with, you know, I'm not actually allowed to plug in -2. Okay. So it's okay if you like walk into the class and you don't really think about this. That doesn't matter. They'll teach this part to you. But I just wanted to give you kind of like a heads up that you're going to hit some integrals where you can't actually deal with the bounds. And maybe to even give you like more of a heads up before ending. So do we feel comfortable with this idea that I'm saying like plugging in -2 is bad? Like I can't do it. So what is a concept from Calc 1 that we use when we can't plug in a number, but we want to see what's happening close to that number? Limits. So in fact, you guys will come to see that when things get a little bit wonky, we're going to use limits to handle it. And rather than dig into a lot of limit stuff right now, we will do some limit review next class. Okay. So, how are we feeling about integration? Do we still have any questions about some of the integrals on that page? Okay. Maybe some people are still thinking about a couple of them, and if you want to, that is great. What I would say for the next little bit, kind of our last activity that I think will really help you feel very confident about U substitution, and it's a technique that you can use when you get introduced to new methods of integration, is I want you guys to create, so here's your task. And if you have more integrals you want to just keep working on, that's fine too. But your task right now, take the next few minutes and create some integrals that you can solve using U substitution. And maybe, see like how creative can you get? Can you make a crazy integral that you are sure is solvable using U substitution? And I promise you, when you go into Calc 2 and you get all these new methods, for each one of those sections, don't need to do this, but you could think about, could I create my own integral that would use this method? And if you can reverse engineer problems to use the methods, then you will recognize when you see the integral on your page, you will know which methods to use. You're like, I can do it forwards, I can do it backwards, I can make these problems. So I think this is a really good exercise. So try to make a couple and share them with neighbors and see like what interesting U substitution problems can you make. Can you make ones with fractions? Can you make ones with trig functions? have made one that you'd like to share, you don't need to solve it or anything. If you want to just come and write just the integral on the board, and then when we've got a couple of them, we can kind of talk as a group about like what we think are good. But yeah, if you made one, like please share it. I can also put one up or something. I'm not the first person.
Oh, I love that one. Would you mind reading that on the board for people?
It's okay. It's okay. Do you, are you working on something? I know I said, but yeah, you like to keep working on. Do you have questions that I can answer those? Okay, this one. How's it going? Have you, oh yeah, this is great. I love it. So what are you thinking about when you like this? Yeah, so like I like this, it's like very clear, right? This, if you want, I think that's a great one. You could put it on the board for us. You made it, you want to share? Wow, wait, this one's crazy. Okay, so you have x to the e instead of x, which is a totally valid thing to use. And technically, x to the e is actually a power function. Yeah, so if you just have x to the e, you can actually just do the integral, like add 1 to the e and divide by e plus 1. So then here, when you have this is actually just a constant still. So like, if you let e be e, the derivative of e is actually c. Yeah, and I know exactly what you're saying. You're like, but the derivative of e. The derivative of e to the x, the function, is e to the x. When I write just e like by itself, that's actually just a number. And it's very confusing because it's kind of like pi. Yeah, so if you were to actually put that, then I actually think you would be making like a super diabolical problem where you would let u be e to the x, but to deal with that x
It's
is
super hard, but then
really
it's sometimes super.
well, the problem I think though is like you're gonna be able to get rid of the e to the x, but how would you get rid of the x on the base? Okay, this x down here, like you'd let u be e to the x, and then you have like x to the u, but how would you get rid of that x? I actually think that's very complicated. Yeah, I don't know, there might be a way, like maybe you have to solve, kind of like Dylan did, you have like natural log or something crazy. How's it going? Have you made one that you want to share, or? Yes. Yeah, no, but I mean, it's this thing where now you're like, every time you see those, you just like, know right off the bat that you do use those, since I'm making those skills very
I
natural.
forgot how to do this.
It's also a good one to share. Oh, but now you're sharing that.
Yeah.
Yeah, cool.
Easy.
Yeah. So working on some. Did you have questions? Yeah, no sweat.
It's digging into
How's it going, Rochelle? Did you have any stuff problem that you'd like to? It's okay. Okay, so you have tangent. No, it's actually, so now you've got the integral tangent.
Oh, no.
And, but you're right, we already talked about that. No, I think that's a nice one. It's kind of like a generalization of the one we were doing before. So I agree, I think that's actually very nice. So if you'd like to write that one. How's it going? You're still working on
Yeah,
problems
just
here?
working
Yeah, that's fine. Do you have any questions?
That's enjoyable.
out there if you want to think about like I think some people have made some really good use of problems, and then what if you were trying to like, I don't know, a use of, what does a use of integral look like that has u equaling a particular function? Like I think we're kind of getting good at knowing when they're polynomials, like what happens and what would live on the outside, but like what would the du look like if we were doing a use of with u equals square root of x? This is a thing you could think about. Did you have, were you talking about
Yeah.
it? Yeah.
What is the first?
Okay.
What is e to the power?
It's just e. It's like 2.712 something.
Can e to the power 0 equal 1?
And e to the power of 0 would be 1.
So like this makes sense.
Okay, so this, you're saying like I would let u be this, and then it would, you know, the e to the x living elsewhere. I think what's challenging here is that oh, I see. So you put this down there. So the one little problem here is that u is a variable that's not necessarily like, when I go to integrate this with respect to u, this x is actually, what is x actually? It's actually like natural log of u. And so what you've really ended up with is like a function that looks like natural log of u to the u power. And because we're not actually integrating with respect to x. Does that make sense? So like, when you, because I know exactly what you're thinking. You're like, well, it may look like x to the u, or u is like really simple. Yeah, no. But I think that was like, that's a really good direction. But the problem is that like one of the sneaky issues when we're doing use of is that you change now, like what does du tacked onto the end mean? It means we're integrating with respect to u. So yeah, so the x is like still there, and I think what's gonna happen, what like horrible thing is gonna happen is that the x is actually gonna be like natural log of u if you solve for this, and then the integral natural log of u to the u is like some kind of you've created a monster, I think. But I really like this idea about where you're letting u be e to the x so that your du is actually e to the x, and you might, you know, maybe you try an e to the x like inside of some other function that is nicer than like power. So like,
I was trying to do like an exception.
yeah, I like it. I think you could try, if you want to plug e to the x into some function, one that might work a little better is one that doesn't involve x, but instead something like square root of e to the x, or sine of e to the x, or, you know, do you see what I'm saying, where like it doesn't actually also involve x, so then you don't have to get rid of that x. Right, and yeah, something like that would be better. But I think you need to be a little bit careful about like you've divided here, and so really you wanted this e to x like be a top or something, right? But yeah, I like the ambition of using e to the x. Which is a good idea. All right, so I sense maybe we're kind of like fading a little bit. That's okay. So let's just kind of maybe like pick out our u's here, and maybe I'll say something about that square root of x and we'll call it a day. So somebody who did not create the integral, does anyone want to say like they think they know which u to use for one of these? Anyone want a second to think about that? What do we think? Do we have any u guesses?
So for the
Yeah.
first one,
Yeah.
the u might be e to the x plus 3.
Okay, and where are you thinking that?
Because when I get the derivative of that, it would be make it easier to get rid of the
Yeah, so that'll get rid of the c to the x, and also it's like plugged in, so it's 4. Yeah, I think this is great.
One, I think it would be sine 2x, sine squared.
Okay, so yeah, so we've got sine squared and we've got cosine. And so you're saying like you think it would be about the sine, not the cosine. Do we want to take like all of the sine squared, or
take the sign.
Just take this line. So like this notation, I think we're used to this, but just to kind of like emphasize what's happening is that this is the same thing as like I'm taking sine and I'm squaring it. This is just like the symbols that we use to write this. But if you think about it like this, it becomes more clear that maybe that sine is like plugged into something. And moreover, what's the derivative of sine? Is cosine. So I agree, I think u being sine x is a really good way to go for this problem. All right, let's hear from someone else. Number 3, somebody have an idea for you? Yeah, Dylan?
10x squared minus 32.
10x squared minus 32, and so can you give us your thought process?
When you get the derivative of 10x squared minus 2, you end up with just 20x.
Yeah, you actually like get exactly this, so this one was also engineered quite nicely to come out pretty good. And what about 4? X plus 7. So what's the idea there? Yeah, it's just 1. So this kind of works out maybe like those, like 5 over x plus 3 for whatever problems we were doing earlier, and then you just have like tangent of u, and we know that we can deal with that. Okay. Questions? We're feeling like, all right, we're gonna go into the semester being like pros on u stuff.
It's a good review.
Yeah, good. Okay, so to be honest, I was told before Sunday, I was told that this workshop went until 3, but I guess it technically goes until 4. So what I will say to you guys is if you are like done with today, because I know that we pushed really hard and really didn't take a lot of breaks, we can stop. And if you had questions, if any of you were like, oh, I still had a couple questions for you, I am available until 4 to talk with you, but you do not need to stay. So let me just give you a heads up about tomorrow. So this is obviously like, this isn't a class, it's not graded, whatever. But what I have to start class tomorrow is a quiz on derivatives and integrals. And so I just wanted to give you a chance. You can do it in teams.